everyone. Welcome to today's webinar, Drones-Based Solution for Efficient Search and Rescue Missions. This webinar is shed light on the groundbreaking project that not only utilizes cutting-edge drone technologies, but also leverage model-based system engineering, MBSE, principle to address some of the most pressing challenges in search and rescue operations. Before we dive into the content, let me share a bit about the structure of this section. We'll start with an introduction to the problem context, explore how MBSE supports our design approach, and finally present our operational plan and conclusions. Please feel free jot down any questions. We'll address them during the Q&A session at the end. Let's begin with a quote from Dr. Robert Goddard. It is difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. This quote beautifully captures the essence of innovation and the spirit of any project. Dr. Goddard's visions remind us that what seems unattainable today may very well be foundation for tomorrow's breakthroughs. It is kind mindset that guided us throughout the development of our drone-based search and rescue solutions. Good. Here is an overview of what we'll be discussing today. Our presentation is divided into 6 sections. First, we'll start with About Us, where we'll introduce the team behind this project. Next, we'll provide an introduction to the concepts and motivations that inspire our work. Following that, we will explore the problem context, identifying the key challenge in traditional search and rescue missions. Well, then transition to the operational overview, where we'll explain the system we've designed. Finally, we'll discuss the implementation of MBSE in this project and wrap up with our conclusion and future work. This roadmap should give you a clear idea of the journey we'll undertake in this section. About that. Perfect. Let's start with our first section, talking a little about who we are. Allow me to introduce myself and my college. My name is Gerardo Ramirez. I am both a firefighter and a final aerospace engineering student at the University of Antioquia in Colombia. My experience as a firefighter has deeply shaped my understanding of the emergency complexities involved in search and rescue missions. My colleague, Juan Felipe Rios, is also a final aerospace engineering student at the same university. Together, we bring a unique blend to practical field experience and combination of skills allow us to tackle challenge from both operational and engineering perspective, ensuring our solution is grounded in the real world needs. Well, we continue with a brief introduction to better understand our context. Let's take a moment to talk about our university. The University of Antioquia, located in Colombia, is one of the most prestigious institutions in the region, with several campuses across the Colombian territory. Among these, the Central Campus in Medellin and Eastern Campus in Carmen de Viboral stand out, with the latter being home to aerospace engineering undergraduate program. It is commitment to academic excellence and research innovation has provided us with the resources and guidance necessary for these projects. The university has a rich history of fostering talent and pushing of the boundaries of knowledge. Our aerospace engineering program in particular is renowned for this focus on both theoretical understanding and practical applications. Being part of the program has been instrumental and enabled us to undertake projects like this one, which aim to address real-world challenge using advanced engineering principles. Okay, one of the key inspiration of this project has been, of course, of model-based system engineering. This course has introduced us to a structured, model-driven approach to designing complex systems. Over the years, students in this course have developed remarkable solutions, such as a high-power rocket models and stratospheric vehicles. Our project focus in drones-based search and rescue operation is another testament to the power of MBSE in tackling a multi-phase challenge. By leveraging tools like Capella, we have been able to model, simulate, and validate our design in a way to ensure reality and efficiency. Why choose MBSE and Capella? Model-based system engineering, or MBSE, represent a paradigm shift in how complex systems are designed. Unlike traditional approach that really heavily on document-based communication, MBSE use models as the primary means of communication and documentation. This approach not only enhanced clarity but also ensured that every stakeholder has the unified understanding the system. In this project, we use Capella, an intuitive MBSE tool that supports the Arcadia Method. Capella has enabled to streamline our workflow from requirement analysis to system validation. This can be crucial, ensuring our solution is both effective and adaptable. Now, after the preamble, now let's get to the understand our project. Now, let's delve into the problem context. Search and rescue missions are inherently challenging. Victims are often stranded in remote, hazardous locations, making it difficult for ground teams to reach them in time. Traditional methods, while effective to some extent, really heavily on manpower, are no, often slow and risky. Delays in response can directly impact in the survival rates of victims, has a crucial time is lost during the search phase. Furthermore, rescuers themselves face life-threatening dangers which can compromise the safety of the mission. Our project aims to address this challenge by introducing a drones-based solution that is faster, safer, and more efficient. Okay, let's discuss how modern search and rescue missions are carried out. In the top left, water rescue teams deploy specialist boats and diving equipment to locate and save people in aquatic environments. These missions often involve rapid coordination and expertise in challenging conditions like strong currents or low visibility. The helicopter in the center represents the aerial rescue operation. These are essential for covering large areas quickly, locating stranded individuals and airlifting both victims and rescuers to safety. On the bottom left, climb rescues require technical climbing equipment, ropes, and trained personnel to navigate steep or hazardous terrains. These missions demand precision, teamwork, often in extreme weather conditions. In the bottom right, we see rescue dogs as a vital asset for location survival in areas where human access is limited or time sensitive, such as collapsed buildings or wilderness zones. Lastly, in the top right image, urban search and rescue missions focus on disaster scenarios like earthquakes, using tools like cameras, sensors, and drones to find people trapped under rubble. Each operation is highly coordinated with teams really out of advanced training and technology to execute a rescue effectively. In our approach, when streamline search and rescue operations by breaking them down into two main phases, the search phase and the rescue phase. This structure ensures that a stage is optimized for efficiency and effectiveness. The search phase is all about accuracy and speed, locating people in difficult environments as quickly and accurately as possible. This is where tools like drones, sensor, and mapping technologies come into play, reducing the time scanning on large and dangerous areas. Once the location is confirmed, we move on the rescue phase, which focuses on safely extracting of victims. This involves careful planning and execution by deploying the rescue drone alongside to rescue will to access the victim. Our approach is not just about splitting up the mission. It is about using technology and well-structured process to save lives more effectively. The flowcharts seen illustrate how these two phases seamlessly integrate, ensuring that every step of the operation is account for an optimized for success. To unify the concepts, some important definitions are present to properly understand the operation. Victim refers up to a person who has suffered harm, damage, or adverse situation due to a circumstance, such as an accident, disaster, or any unexpected or harmful event. Patient refers to a victim who has had direct contact with rescuers. In other words, a victim becomes a patient once they are in the care of the rescuers. Checkpoint refers to a control point or a strategical select location near the area used to ensure the progress or status of the operation. And in the next section, we begin to break down the operation. Let's start by defining in the context of Capella what an operational entity and operational actor are. Operational entity, a real-world entity such as an organization and or system that interacts with the system being started or with the users. An operational actor, a human indivisible entity within an operational entity who has a specific role in the operation, e.g., a pilot or an operator. In our case, we have two operational entities. Rescue base, this is the place where all equipment is stored and where rescue rests, similar to a fire station, and ambulance. And five operational actors. Rescuers, individuals trying to in rescue techniques and first aid. Ground operators, responsible for coordinating the operation to ensure it is carried out safely and efficiently. Logistic team, ensure everything functions properly and that all necessary resources are available. Technicians in charge of maintaining equipment to ensure it is always operational. And finally, paramedics, part of the ambulance entity, responsible for keeping the patient safe while they being transported to a medical facility. Good. The search system is a key component of our solution. Using drones equipped with advanced sensors, the system locates victims in hard to reach areas after taking off from a control station. The drone follows specific search patterns and descend to a set altitude to ensure accuracy. Once the victim is located, the drone sends the coordinates to the control station, enable a quick response. For this purpose, we recommend using the DGA matrix 300 RTK, a drone now for its reality and precision. It is important to note that this part of the system will not be developed in-house, but instead, we will seek a commercial solution that meets the operational needs. This decision has made give that drone development has already reached a very advanced stage, making it is necessary to develop from scratch. The rescue system, for its part, is specifically designed for the patient extraction phase. With our main focus, this system is based on the development of urban mobility as a rapidly growing field to provide innovative solution in emergency situations. It consists in a high-capacity drone capable of carrying it is on weight and transporting two rescuers equipped with the eight tools. The drone is capable of reaching the victim's location and advanced obstacle avoidance technology, allowing to navigate safely in a complex environment. By integrating these features, the system not only ensures the safe transport of victims, but also minimize risks for both of rescued individuals and the rescuers, enhancing the effectiveness of the rescue operations. This innovative approach leverages the latest trends in drone technology and aerial mobility, positioning the system as a cutting-edge solution for rescuers in hard-to-reach areas. My colleague will continue with the explanation of the process following for the scene of the system.
Okay, now we are going to focus in the MBSE implementation. And to start, we would like to talk how the Arcadia method has helped us in our development. The first is to truly understand the problem to be solved, what needs to be addressed, and how the development process can be get based on that issue. This method enables defining and designing the system's architecture collaboratively among all engineering actors. The goal is to ensure that all disciplines are considered in the architecture design. And the use of digital models allows for early stage validation, making the process more efficient, reducing development time, and lowering costs. And one of the best aspects of this method is that the initial focus is on the system's needs and operational analysis with with functions and progressively formalizing requirements based on these needs. Okay, so we are going to start with the operational analysis, with the operational architecture diagram or breakdown. This diagram represents the functional architecture of the UAV-based rescue systems, highlighting interactions between rescuers, ground operator, technicians, logistic teams, and paramedics. Implementing this model in Capella within an MBSE approach ensures the involvement of all actors and the effective integration of key technologies, such as search and rescue drones equipped with thermal sensors, high-resolution cameras, and AI algorithms. Capella facilitates validation and coordination, optimizing real-time decision making and interoperability between systems. This is crucial for reducing response times and maximizing mission effectiveness in complex environments, ensuring all teamwork together seamlessly to locate, stabilize, evacuate victims efficiently. So let's see the actors and the entities that we have. The first rescuers, they are responsible for reaching and extracting victims, assessing their condition, stabilizing injuries, ensuring safety, and reporting progress to ground operators. Also, we have ambulance and paramedics. They provide medical care, transport victims to safety facilities, and ensure that medical equipment is clean and ready for future emergencies. Also, we have technicians. They maintain and update equipment, software, and maps to ensure proper functionality. We have ground operators. The ground operators oversee rescue operations and coordinate with other teams and ensure compliance with safety protocols. There is a logistic team. They manage the equipment, transport, allocate necessary resources, and the rescue base provides housing for personnel and securely stores equipment functioning similarly to a fire station. This process, derived from the OAV, focuses on the rescue operation, assuming the rescue drone has already located the victim. And defining operational processes like this is crucial as they help identify system requirements needed to achieve mission success. The operation starts with the access and extract the victim phase, where rescuers follow pre-trained protocols, and once stabilized, the victim is extracted and transferred to paramedics in the ambulance for transportation medical to a medical center. After patient delivery, the operation continues with equipment maintenance, cleaning, inspecting for damage, and ensuring readiness for future missions. And finally, the equipment is securely stored, prepared for the next operation. Following with the operational analysis, we had mode and state machines. Capella's MSM diagrams are essential for providing a clear structure view of systems dynamic behavior. They model how the systems responds to events, transitions between modes and states, and ensure synchronization among components. This diagrams offers several advantages, like clarifying systems behavior by visualizing how it operates under different conditions, identifying errors early by detecting inconsistencies, ambiguities, or gaps in the design before implementation, reducing costs and development time. Also, coordination subsystems to ensure seamless interactions and state transitions, and supporting testing and simulation, serving as a foundation for validation scenarios. So here we have a global MSM. This diagram represents the system's operational stages or modes. Each block that we can see represents to a primary system state. It corresponds to a primary system state with transitions driven by event or conditions. So the first block is waiting. Here the system is on standby, is ready for activation in case of an emergency. And from here, it transitions to deployment when a rescue mission is triggered. In this state, drones and resources are sent to the designated search or rescue area. And once positioned, the system transitions to search state. In the search state, the system actively searches for victims using drones equipped with sensors like thermal cameras, GPS, and others. And if a victim is found, it moves to rescue mode. In the rescue mode, the extraction and stabilization of the victim take place. Teams work to complete the mission, evacuate the injured. And the final block is maintenance. Is the final stage, ensuring all equipment is in an optimal condition for future missions. And once maintenance is complete, the system returns to waiting, ready for the next operation. Here we have the search MSM. To start, the first block is idle. The drone remains active, waiting for a mission assignment. It remains in a passive mode until an emergency or a situation requiring intervention is detected. Later, there is a flying block. Here, the drone is deployed and flies toward the assigned area. This say represents the transition phase toward the target area. Later is the detecting. The drone uses its sensors, thermal, visual, and others to search for a possible victim. In this said, things of victims are identified in the search area. Later, we have a reporting block. Once the presence of a victim is confirmed, the drone sends a detailed report to rescue team. And this is crucial for validating the location and conditions before proceeding with the extraction. Also, we have returning after completing its mission. The drone returns to its base or designated area, and final marks the end of the search mission cycle. Here we have the rescue MSM. We also have an idle block where the rescue drone remains on standby until the search drones provide a victim's location. We have a preparation of rescuers. The rescue team prepares equipment to assist the victim. Later, flying to victim where the drones transport rescuers to victim's location. Rescue operations where the team performs the necessary procedures to extract the patient safely and quickly. The returning where the drones transport the patient back to the base where paramedics take over for hospital transport, and also the final marks the conclusion of rescue mission. Here we have a global MSM and MSM coordination. This diagram represents the fuel rescue process starting from the emergency call and that triggers the operations, and the sequence progresses throughout the deployment, victim extraction, medical transport, and system maintenance, ensuring readiness for the next mission. Now we are going to start with the system analysis, but to start, it's important to clarify that the operation is divided into three main missions that we can see. The first is provide victim search. In this mission, the system locates the victim, and once the location is confirmed, the process moves to the next mission, that is provide patient extraction. Here, the rescue drone and rescuers stabilize and extract the victim, and the patient is then handed over to paramedics for hospital transport. And the final mission is provide transportation to the medical center. The victim is transported to a medical facility for further treatment. Here we have the system architecture diagram or breakdown. This diagram is critical because it defines system functions, enables subsystem division. It helps establish interactions, analyze information flows, and identify potential design gaps, such as missing or incomplete functions. As shown in the diagram, the primary focus is the rescue drone. External actor includes the ground station and rescuers who interact directly with the drone. Since the drone will transport two rescuers to the victim's locations, it must have VTOL capabilities, introducing design constraints that must be considered. VTOL, or vertical takeoff and landing aircraft, is an aircraft that can take off and land vertically without the need for a runaway. Additionally, it can hover. Hover is maintain stationary flying in mid-air. And another fundamental function of the drone is autonomous control. This is achieved through some that we call situational awareness, relying on sensors such as LiDAR and cameras to avoid obstacles and follow a designated route to its destination. However, it's important to have solutions if there is a problem. So we have as a backup, the drone can be operated remotely by an operator at the ground station. For this is necessary a live video transmission along with continuous monitoring the drone's status from the ground. And this is achieved through the transmission of flight parameters, environmental conditions, subsystem status, and more. And another crucial aspect is the transportation of life support elements, such as the stretcher, which must be deploying following the rescuer's instruction. Now we follow with a logical architecture and considering these functions and additional ones that arise throughout development, we define the main subsystems, which are communications, navigation and control, avionics, power plant, propulsion, payload support, and structure. This is done through the logical architecture diagram or breakdown by dividing the system into subsystems. We cannot only see the functions of each subsystem, but also their interactions. These interactions allow us to establish a logical flow for different internal activities that the drone must perform. This helps us to identify failures at the interaction level subsystems and support decision making during the design process. And finally, we have the physical architecture diagram or breakdown, the PAB. This defines the physical architecture of the system, specifying the real components that implement the function described in the LAB. It mainly helps us to identify the necessary physical components for the drone, relate each component to its function within the system, and understand the interactions between the different subsystems. While the LAB is conceptual and describes what each part of the system does, the PAB explains how these functions are physically implemented. In our case, the PAB facilitates the selection of appropriate hardware to fulfill the system's functions, allows us to plan the integration of physical components, ensuring compatibility, and helps identify potential failures related to hardware and its connections. Now let's take a closer look at these subsystems. Let's start with communication subsystems. This subsystem only requires an antenna capable of receiving and transmitting information to the ground station, along with its respective control unit. For this, we use MATLAB and Python to calculate antenna gains and range. And the navigation and control subsystem is critical. It includes cameras, a LiDAR sensor for precise obstacle detection, and a controller that transmits information to the communication subsystems. Additionally, this controller manages interactions and data exchange with other subsystems. Here we have the power plant subsystem. This is one of the most developed subsystems that we have through extensive analysis and modeling using Python and MATLAB and Simulink. We conclude that the most efficient and effective solution for this drone is a hybrid system. It consists of a combustion engine powering an electric generator, which supplies energy to all subsystems. And additionally, backup batteries are included for use in case of failures. And the payload support subsystem includes a controller that receives instructions on when and how to activate the system. And using an electric winch and a retractable cable, it raises lowers the stretcher as needed. Okay, finally, we have the avionics subsystem, which acts as the brain of the drone. This subsystem houses various sensors that continuously monitor the status of all subsystems, environmental conditions, and flight parameters. All this data is then sent to the ground station through the communication subsystems. And the propulsion subsystem, for this subsystem, we use tools such as OpenVSP, which allows us to create aerodynamic models of the drone. And after testing various configurations, we determined that a quadcopter design was the most efficient. And additionally, simulations in MATLAB demonstrate that a coaxial configuration will be the most suitable, as it increases the propulsive disk area and serves as a constant backup in case of rotor failures. Okay, conclusions. We can say that the use of model-based systems engineering proved to be a powerful methodology for structuring and managing the complexity inherent in both the drone's operation and its design. By adopting a model drawing approach, it was possible to establish a clear and organized framework that facilitate decision making, optimize systems integration, and improve communication among different actors related to the operation. Leveraging Capella and a comprehensive traceability was key, ensuring that every design decision remained aligned with the initial requirements and the operational needs of a rescue mission. This traceability played a crucial role in validating the design and as it enabled continuous verification that the drone's main functionalities effectively address the demands of search and rescue operations. By maintaining a direct link between high-level requirements and their corresponding implementations, the integrity of the systems was preserved throughout the development process. Furthermore, the model-based approach enabled a modular drone architecture, allowing each subsystem to be independently upgraded or replaced without significantly impacting of the overall systems. This modularity enhances the scalability and maintainability of the drone, making it adaptable to future technological advancements or mission-specific modifications. Such flexibility is particularly beneficial for rescue operations where involving challenges may require integrating new capabilities such as improved some communications and add more navigation technologies maybe in the future. The current design approach successfully meets the established operational requirements, ensuring that the drone performs efficiently under real-world rescue scenarios, as we could see in the mode and state machines. Its architecture provides the necessary reliability, maneuverability, and robustness to operate in challenging environments such as remote or hazardous areas where traditional rescue methods are limited, as we can saw. Finally, the developed drone serves as an effective aerial rescue system, fulfilling its primary objective, providing a swift, reliable, and safe solution for the evacuation of injured individuals in hard-to-reach locations. By precisely integrating all the subsystems, the drone is capable of executing critical rescue missions with high efficiency, demonstrating the value of MBSE in the development of complex airspace systems. For future work, we would like to perform the validation and verification of the system, ensuring that all functional and performance requirements are met. This is a very important process, and by applying MBSE-based verification techniques such as requirement-based testing and simulation validation, we can confirm that the drone behaves as expected under various operational conditions. Another crucial step is the modeling of operational scenarios to identify potential failures or areas for improvement. We could see these scenarios in the MSM, but okay, we have those scenarios, but it's important to model these scenarios to identify these potential failures. And additionally, the development of a physical mockup in the future, we would like to do it. This will be an essential milestone for verifying the integration of the main components. In that stage, the drone doesn't need to be fully functional, but rather serve as a structural and spatial prototype to verify that the design is correct. Okay, thank you so much. If you have any question, we will answer.
Okay, great. Thank you very much, Juan, Felipe, and Gerardo for this webinar. I think it was very interesting. Let's go with the first question. So the question is, did you consider in your modeling interaction with other air assets, such as helicopter? These are often working in parallel, and airspace conflict is an important consideration for drone operation in search and rescue.
Okay, no, we had not considered joint operation with helicopters in our modeling. Our focus has been on the drone operations as a primary aerial asset, aiming to reduce the dependency of helicopters. However, we recognizing the importance of airspeed, airspace conflict management, and would consider the integration this aspect in future developments to enhance the operational safety.
Can you give more precisions on your role and your position in the context of rescue missions?
Okay. As my partner said in during the presentation, we want to attack some scenarios, specific scenarios that are very common, mainly in countries like Latin America, mainly in Colombia. That is where we are. Hard scenarios where, and complementing the last question, where helicopters can go. So we propose another solution for those zones, maybe more, maybe not close to a urban context. And our role is supply this problem, attacking maybe these areas of hard access.
Congratulations
on the presentation. Did you model the operational capacities?
Yes, we conduct a simulation for key subsystems such as communications, power, and propulsion. This simulation allowed us to evaluate the operational capabilities, yes, of the drone under the different rescue scenarios, ensuring that the critical components perform effectively and reality in real world conditions. For this simulation, we will use MATLAB, Python, VSP, no more. This is the only programs.
Very interesting application of MBSE, but I have a comment. I'm always amazed to see very linear process models, i.e. rescue operational process, global MSM, rescue MSM, as if everything were happening in an ideal way. Shouldn't it be necessary, even at a high level of abstraction, to foresee the events that will cause processes not to work
Okay,
according to a
I
nominal
can read
scenario?
the question.
Otherwise,
You
how
are
can you be sure
absolutely
that the
right.
model is built in a realistic environment?
Yeah, you are absolutely right. We present the process modeled in a more linear and straightforward way to make. Acer, this form is present for Acer to understand for a diverse audience. However, we are in need consider non-nominal scenarios in our development. We recognizing the importance of a coating of for unexpected events to ensure the model's viability in realistic environments. And this part of future work.
Did you use a tool to integrate the results of OpenVSP or Simulink to the MBSE architecture?
Not yet. We want to integrate some models in a central way. We use OpenVSP to make simulations, aerodynamic simulations, and we could see with different simulations that the quadcopter design was the most efficient. But in these moments we haven't use a tool to integrate.
Did you consider the non-functional requirements such as cost, weight, flight time, weather limitations, sensor quality, etc. in any way within the model?
Sure, we have all these requirements. After the presentation, we will send you a GitHub where you can see all these requirements. Weight is, how many is the weight? 300
Yeah, 300
300 kilograms. Flight time is 40 minutes.
40 minutes.
What are limitations? We are making the design considering the worst scenario with in the wind, in the weather. So we are considering it in the design. The sensor quality is more in the future, that we can focus we can focus in each subsystems with the sensor that we are going to use. But the sensor quality not yet, but we also have the other requirements.
If the drone is the system of interest that you are specifying the requirements and developing the architecture for, why did you choose to develop concepts, for example, drone states of the drone in the operational analysis?
It's very important to understand all the scenario, because we are proposing a solution for a specific problem. So we need to consider all the operations. So we saw some drones, search drones was necessary for the operation, but in that process we could see that it's not necessary to design the search drones, because we can obtain drones for this solution in the market. But the rescue drone is not in the market for this solution. So we in this stage are focusing in this design and development, because is the another part to that we need to complete the solution, the operation for this problem that we are attacking.
How exactly did the Python and MATLAB help your model? Can you mention which areas of Python were used?
MATLAB was used for numerical simulation, particularly for the modeling and analyzing the drone subsystems. Python, on the other hand, was used for data visualization, allowing us to present the results and accessible in full way. The combination of both tools help to understanding the system performance and help to generate the requirements for the system in general.
So thank you very much for presenting this webinar and for sharing your work, Juan, Felipe, and Gerardo. And thank you to all of those who are attending this webinar.